Yeah, thank you. And thanks to Felix and the organizers for the invitation. I hope the audio is okay. Yeah. So, yeah. My talk is based mainly on these articles, which I show here, in particular the first one, together with Albert Much, the speaker of this morning. And yeah, so this is the outline. I will skim over the algebraic quantum field theory framework. Then I mention Sorkin's impossible measurements or operations in quantum field theory, which address the problem of superluminal operations in quantum field theory. And then the ping-pong ball test is to indicate that the similar kind of problems also arise in classical field theory. So they're not specific to quantum field theory. And then I will very briefly give a glimpse of the quantum measurement approach by Chris Fuster and myself, where these problems are avoided. Okay. So what is a ping-pong ball test? So the ping-pong ball test is captured in this phrase up there, which I learned from Reinhard Werner. When someone presents a paradox as being rooted in quantum physics, replace the term quantum mechanical particle by ping-pong ball everywhere. If the paradox persists, it is unrelated to quantum physics. This is very useful. You should teach that to your students of quantum mechanics. So now algebraic quantum field theory. We have an algebra of observables, which you can always think as subalgebras of some B of H. And usually we take these local algebras of observables, and you can think of them as generated by bounded functions of field operators, quantum field operators, observable quantum field operators, where the support of the test function is in the space-time region O. So I'm thinking here of Minkowski space-time. One can do this for more general spacetimes, but for our purposes, it's sufficient to think of Minkowski spacetime. Okay, then one has certain properties which I've listed here. This isotropy relation, causal disjointness of the localization regions leads to commutativity of the respective operators. And then there's also a covariance requirement, which is fairly obvious. And this is, if you like, the operator algebraic version of the Weidmann axioms according to this rule. In quantum field theory, the typical situation is that these local algebras are really weakly closed star subalgebras of some B of H. The set of physical states then is given by the density matrices, like so, and the action of space-time transformations is implemented by unitary group representation. There's then also a unit vector which represents the vacuum because it's left invariant by all these space-time transformations. And the time translations in any Lorentz frame are implemented by an associated unitary group where the generator, the Hamiltonian if you like, has a non-negative spectrum. Okay, so this is the setting which I will adopt. Now, if you are versed in quantum information theory, then you know what A channel is a transformation on the observable algebra, which in Krauss form looks like that. And the channel is non-selective if it's unit preserving, and it's localized in a space-time region if it maps the algebra of the space-time region into itself, and in the causal complement it acts trivially. And then there's the dual of a channel, which is called operation. Yeah, and it's really the dual, the little omega or the states. And then an operation is called localized if the respective inducing channel is localized, or non-selective if that is the case for the inducing channel. We will need this generality at some stage. And the simplest example in quantum field theory, or also in quantum mechanics, of course, is that you have a unitary in your observable algebra, maybe it's even in a local algebra, and you take the adjoint action of this unitary. So, and then you see if the unitary is taken from this OA local algebra, and you now take observable SPI from a local algebra with a localization region which is causally disjoint from the region OA, then you measure no effect on applying the operation induced by this unitary because you have commutativity. Okay, this is very simple to understand. Now let me address the impossible measurements or impossible operations scenario, which has been pointed out by Sorkin already some time ago, as you can see. So here we have three space-time regions, which are arranged in this way. So here is the space-time region of Alice, which you can think of as the laboratory that Alice has control over, then Bob's region and Charlie's region. You see the regions of Alice and Charlie, they are causally disjoint. And this intermediate region of Bob, this has some overlap with the Alice region and the Charlie region. So there are some double cones which lie in the respective intersections. And now the point is, since the Alice and Charlie regions are causally disjoint, Charlie cannot know by measuring in the Charlie region if Alice has carried out a unitary operation in her laboratory, because of the commutativity of the U and the C. Yeah? But if first Alice carries out a unitary operation and then Bob, there can be differences now because the U that you have need not commute with either C or either U Alice. So, and you can in fact give examples where you can now see a difference where you can check if Alice has actually carried out a unitary operation in her lab when afterwards Bob carries out a unitary operation. So Charlie can check this using appropriate observables. So, and now Sorkin has argued, well, this would mean a superluminal transfer of information since Alice and Charlie are causally disjoint, but Charlie can nevertheless check if Alice has carried out an operation. So there are certain examples in quantum field theory given where this inequality really occurs. And of course, that amounts to this operation by Bob now implementing superluminal communication between Alice and Charlie, and this is unphysical. Now, what I would like to point out here is that such superluminal communication channels arise also in classical field theory by local kinematical symmetries. So here is the theorem which is in our paper, or the result. So you can phrase the theory of the classical Klein-Gordon field also in terms of observable algebras, yeah, as you can do with any theory. This is maybe not the usual approach, but you can do this in complete parallel to the treatment of the quantized Klein-Gordon field. So we do this here. So the A of O are now either the local algebras of observables for the quantized or the classical Klein-Gordon field in their respective algebraic setups. And the statement is, then there are states and operations for Alice and Bob respectively, together with observables that Charlie can choose, so that Charlie, by measuring with suitable observables in Charlie's localization region, can distinguish now in this setup if Alice has carried out an operation or not. Specifically, this operation of Bob can be chosen so that it corresponds to an instantaneous rotation about the x3 axis by 180 degrees, which flips the O minus and O plus double cones in these intersection regions. I'm showing the picture in a minute. And for the quantized Klein-Gordon field, there is also a unitary operator in the local observable algebra of Bob, which implements this, if you like, local rotation. One can show this rigorously. So here is the picture again. So here you have these two double cones, if you like, in the intersection regions of Bob with Alice on the left-hand side and Charlie on the right-hand side. And now a rotation around the x3 axis would exchange these little double cones. So, of course, this is pictured more easily if you add one space dimension. Then the double cone has here such a form, and you have these double cones here, left and right, and you rotate it in that x1, x2 plane by 180 degrees, and they are exchanged. Yeah? And in the theory, you can perform, in quotation marks, this rotation such that it takes no time. So you have an extremely fast carousel, as fast as you like. So these are elements in the theory, and of course, these are kinematical symmetries. Huh? They are not dynamical. You cannot perform them in the real world. Yeah, so remarks here. This approach of describing classical field theory in terms of local algebra, in terms of the local algebra framework, you can find in the literature. So it has been developed in particular by Brunetti, Dütsch, Fredenhagen, and Reisner. And in these two monographs, it is also outlined. Of course, in the classical case, these operations are not induced by unitary operators in the local algebras. Because in the classical case, the local algebras are commutative algebras. They are basically some choice of functions on the classical phase space. Huh? However, the generator of this operation can be obtained with the help of a Peierls bracket which generalizes the Poisson bracket of Hamiltonian mechanics. You should know what it is, because you know the angular momentum operators. Okay, so now I very briefly address this FV framework, which stands for Fewster and myself, and has come to be called like that in some literature. And the idea here is, well, it's related to actually measurement, quantum field measurement. And what it does is it provides a covariant, relativistically covariant measurement scheme or measurement protocol. It does not solve the measurement problem. So if you say, well, the measurement problem, a solution should be that we understand the transition from quantum to classical. No, we don't address this at all. We are just interested in describing quantum measurement dynamically, so by local interaction, in a way that is relativistically covariant. So it really fits with the rules of relativistically covariant and causal quantum field theory. Okay, so the starting point is the idea that we have two quantum field theories. One is A, which we call the system, and the other is P, which is the probe. And we can combine these into a joint system, joint quantum field theory, by taking here a formal tensor product, which in the Hilbert space representations you can also make completely rigorously. And then there are the corresponding local algebras. So basically, we just have two quantum field theories at that point. And the idea is measure observables of the system by coupling the system dynamically to the probe in a specified interaction region, which is called O index I for interaction, and measure the observables of the probe. So and at that stage, you may wonder, why so complicated? And well, actually, this is a common procedure in elementary particle physics. If you think that usually what you can measure very effectively and precisely and cost efficiently are photons and electrons, maybe also sometimes protons, sometimes even magnetic moments of neutrons and so forth. It's already quite complicated. But I mean, for instance, what do you do to measure neutrinos? You do not have a direct neutrino detector. You cannot look at the instrumentation catalog and neutrino detector, please. No. You basically first have to couple the neutrinos to other quantum fields, as happens in the beta decay or inverse beta decay. So electrons and photons come into the game, and those you can measure. So in this picture, the A, the system, would be a quantum field theoretical description of neutrinos, and P, the probe, would be whatever you like, photons, quantum field theoretical description of photons. For photons, you see, well, you probably really need quantum field theory because they are inherently relativistic things. Okay, so now the effect of the coupling, the dynamical coupling between the two, system and probe, the degrees of freedom is described by a scattering morphism, which we call capital theta. And under general conditions, this is given by the action of an S matrix, as you would describe it in scattering theory and quantum field theory, now for two types of quantum fields. A very helpful assumption here is that the interaction is only active in a bounded interaction region OI, of space-time. That means over finite time and over a compact region in space, which you can arrange. Often it is arranged for you naturally because elementary particles only have a very small interaction range. So this is something which is not exotic at all. And now the scattering morphism can be shown to exist quite generally, and its localization properties can be derived if all the quantum field theories obey the time slice property. So the time slice property says that under certain conditions, the algebra of a smaller space-time region actually already is the algebra of a larger space-time region. And this is this picture here, the time slice property. So you have, well, you have here a space-time region in red, which is a neighborhood of something like a Cauchy, local Cauchy surface, namely the Cauchy surface for a larger double cone in green. And then the idea is here that the observable algebra of O tilde, the larger double cone, is actually the observable algebra of the smaller one. Yeah? And actually this holds for all linear quantum field theories, which are subject to a hyperbolic dynamics under very general circumstances. It's the idea that solutions of wave equations are determined by their Cauchy data. This goes back to this, but also it has been shown in perturbative quantum field theory, at least some perturbative quantum field theories, by Chilian and Fredenhagen in 2009, which uses the setting of perturbative algebraic quantum field theory. And here you see the power of the algebraic methods, also when you apply them in the perturbative setting. Now, using this, you can derive localization properties for the scattering morphism, namely, it is trivial outside of the causal complement of this coupling region or interaction region OI, and it preserves causality in some way, because if a region O plus is not in the causal path of OI, like here, it's not in the causal path. The causal path of OI would be here lying inside these green bars here, causal path. And if O plus is not in the causal path of OI, then theta maps the algebra, the joint algebra of system and probe, in O plus into the causal path of O plus. In particular, it does not, let's say, here, if you think over here lies O Alice, this here is O Bob, and this here is O Charlie, then you see there's no overlap here with the O Alice region. And this is very instrumental. Yeah? This prevents these non-local operations. Okay, now we frame the Sorkin scenario in this approach to measurement. So we have now a joint probe, which is this product of the Alice probe and the Bob probe. And the interaction region is the union of the interaction regions that you can think of are the labs of Alice and Bob. And here the region of Alice does not lie in the future of Bob. And then an interesting result in our paper is that under certain very general assumptions, the scattering morphisms can be separated or concatenated as you wish. So we have one scattering morphism of Alice. This is this one. So this combines the probe of Alice and the system, and the in-between is neutral. Yeah? This is where you insert a unit operator, nothing happens. And on the other hand, you have the same for Bob. Bob only then interacts with Bob and Charlie, and you insert a unit in the first slot or the Alice slot where nothing happens. Now, yeah, this is this assumption, causal factorization of the coupling dynamics, like so. For this, it is important that the regions of Alice and Bob are situated in a particular way so that Alice does not lie in the causal future of Bob. You can, now you can reformulate that in this way, namely the corresponding operations on the states, they have this, if you like, separation property. The combined so Tor, the full operation is really this combined operation. This causal factorization of a localized dynamics is typical in quantum field theory. It is a variant of Bogoliubov's formula. So this is very natural when you have point-like interactions. Yeah, okay. Here you see the probes of Alice and probes of Bob are prepared in certain initial states prior to the interaction, and there is also a state of the system part of Charlie. So, and through the dynamical interaction, they get combined. Yeah? So after the interaction, they usually build up entanglement or correlations, so they are no longer of the product form. This is why you can hope to measure the system by measuring the probe. After the dynamic coupling has taken place. Okay, so here is this theorem, related theorem by Bostermann, Fuster, and Rupp. I state it here for you. So let the space-time regions of Alice, Bob, and Charlie be as before. Suppose that Alice and Bob use probe quantum field theories, P Alice and P Bob, to couple to the system quantum field theory A. The interaction regions are the labs of Alice and the labs of Bob. Alice and Bob have prepared the states of their probes, sigma Alice and sigma Bob prior to coupling. And then if Charlie applies an observable after the coupling has taken place, then you can investigate what happens if you apply this combined operation of Bob and Alice to the joint state, and you measure on the side of Charlie, then you see that actually this operation of Alice drops out. It's not noticed. That is due to well, basically you have a causal interaction which does not give you this superluminal information or transformation within the localization region of Bob. Okay, so yeah, I've said this already. So conclusion, the impossible measurements, respectively operations scenario, so you can say measurements are certain operations, yeah, does not only arise in quantum field theory, but also in classical field theory. And this is the ping-pong ball test. Yeah? So we have replaced a quantum field situation by a classical field situation, and we have noticed, okay, they lead to the same potentially problematic phenomenon. This is not specific to quantum field theory. Huh? Nevertheless, there arises a problem, namely, for instance, you have kinematical symmetries as potential operations associated with the local algebras. And, well, they are not physical. You cannot carry them out. Huh? So you would have to, you would have to rule them out. And one way of ruling them out is to say, well, follow our protocol. So measurements should be induced by local and causal couplings to probes. And if you do that, then you don't run into this problem. It doesn't occur. Yes. So, yeah, this is what I had to say.